and welcome to another WJEC A level physics question. This was question 4 from June 2014's Unit 5 paper, and it's a magnetic fields question, and magnetic fields is nowadays in Unit 4. For part A of the question, we're told that we've got a solenoid of length 1.45 meters with 9,560 turns. And we've got to find the magnetic field strength, the flux density inside the solenoid when the current in it is 320 milliamps. So equation is given in the data book, B equals mu naught Ni. Mu naught is 4 pi times 10 to the minus 7. N is not just the number of turns, it's the number of turns per unit length. So the N is the number of turns divided by the 1.45 meters. And then multiplied by the current of 320 milliamps. A little tip here that if you put 4 pi times 10 to the minus 7 directly into your calculator in that form, your calculator will throw a bit of a wobbly, it won't like it, and come up with a syntax error. One way around it is to type 4 pi, then times, and then the times 10 to the x button, and then it will work properly. If we put those figures into a calculator, we end up with 2.65 times 10 to the minus 3 Teslas, or 2.65 milliteslas. And it was actually a unit mark question here, so as always, never forget the units. For part B, we've got to calculate the resultant magnetic field strength halfway between two long wires shown in the diagram, and we've got to state its direction. So first of all, let's consider B1, which will be the field due to wire 1. Formula again in the data book is mu naught I over 2 pi A. So it's going to be 4 pi times 10 to the minus 7 times 0.24 over 2 pi times 1.7 centimeters, because we're looking at the midway point between the two wires. A little tip here is cancel the 4 pi with the 2 pi, so you just get away with that little calculation problem with a 4 pi times 10 to the minus 7. If we put those numbers into a calculator, we end up with 2.82 times 10 to the minus 6 Teslas. Now before we move on to work out the field due to the wire 2, let's work at the direction of that field. The direction of that field is worked out by using Fleming's not Fleming's right hand rule, just the right hand grip rule. If you point your thumb in the direction of the current, in this case this current pointing to the right of your right hand, you'll find that underneath the wire your fingers are curling into the page, and we can represent that by a little circle with a cross in it, where the convention is that that cross is like the flights of a dart moving away from you. So this field is into the page. Similarly, we can calculate B2 with the same formula. So once again, we've got 4 pi times 10 to the minus 7 times 0.37 over 2 pi times 1.7 times 10 to the minus 7. And the answer to that, once we put the numbers into the calculator, will be 4.35 times 10 to the minus 6 Teslas. Again, if you point your your thumb of your right hand in the direction of that current, at the place in between the wires, you should find that your fingers curl out of the page. So B2 is out of the page. So what we've got here are two fields, a weaker one, B1, into the page, and a stronger one, B2, out of the page. So remembering that fields are vector quantities, we can find the resultant field simply by subtracting the two answers. So the resultant field, let's call it B res if you like, is going to be 4.35 times 10 to the minus 6 minus 2.82 times 10 to the minus 6. And that will be 1.53 times 10 to the minus 6 Teslas. And seen as the stronger field was out of the page, the resultant field will also be out of the page. For part C, we've got to calculate the position between the two wires where the magnetic field strength is 0. So fairly clearly that's going to be closer to the top wire. So let's mark this distance here to the top wire, I'm going to call it X for argument's sake, and therefore the distance from the bottom wire is going to be 3.4 minus X in centimetres. At that point the two fields will be equal and opposite, so we can equate expressions for both fields. So what we will have is mu naught I1 over 2 pi x will be mu naught I2 over 2 pi with 3.4 minus x. And I can leave that in centimetres so long as I remember that my final answer will be in centimetres. Let's do a load of cancelling. Get rid of the mu naughts, get rid of the 2 pi's. And then let's do a little bit of cross multiplication. We're going to have I1, which was 0.24, 0.24 amps, times 3.4 minus x will be equal to 0.37 for I2 times x. We can either expand the brackets here or divide by both sides by 0.24. Let's go through the expand the brackets method. So 0.24 times 3.4 will give us 0.816. If we gather the x's all on the right hand side, we're going to get 0.816 equals 0.37x plus 0.24x. So altogether we've got 0.61x. So let's write that the right way around. 0.61x is equal to 0.816, and then x is 0.816 over 0.61. And that will give us 1.34 centimetres. And just for clarity, I'm going to put from wire 1, just to make it clear. I've already labelled it on the diagram up here, so it should be obvious that that's the distance. But always do make sure that you make it clear which wire that distance is from. Thank you very much for listening. Please remember to like and subscribe, and feel free to ask any questions. Goodbye.